Okay, hello everyone. This is Xiaoming. Today I will give a presentation about our ICML 2024 paper, Agent Smith. A single image can jailbreak 1 million multimodal large language model agents exponentially fast. So let's get started. I believe all of you have heard about the movie The Matrix. Actually, Agent Smith is the character in this classic movie. Here is a clip for this movie. Let's enjoy it.
You. Yes, me. Me, me. Me too.
So in this movie, Agent Smith, like a virus, it can infect others to become itself. So actually, our paper draws the inspiration from this movie or the infectious disease that whether we can design a variant which can infect other agents, and this spread can be exponentially fast. Okay, before introducing our work, I want to give us some background knowledge to this paper. The first one is that we want to define the agents, right? With the popularity of large language models, they become an integral part of AI agents. These agents can behave like humans. Like in this diagram in here, that these agents have the memory, they can leverage external tools, and they can make plans, and also take actions like humans, just like humans, right? Here example for this large language model-based agents that these agents can be adopted in the Minecraft game. As you can see here, these agents can automatically take some action like swim, catch fish. Yeah, hunt and pig, etc. Okay. So all these actions are generated by these agents themselves without human perturbations. Okay. Here is another example about now we have the single agents, and the next level is a multi-agent environment, which means in this environment there are multiple single agents, and these agents can interact with each other, and they can perceive the surroundings and make the decision together. Okay, let's see the movie.
How might we create an artificial society that reflects human behavior? In our paper, we introduced generative agents, software agents that simulate believable human behavior. To demonstrate, we instantiated 25 generative agents to populate a game town inspired by The Sims. In it, these agents wake up in the morning, cook breakfast, and head to work. They socialize and reflect on their past as they plan for the future. To enable generative agents, we contribute an architecture that extends a large language model to store and make sense of the agent's experiences. Our evaluation shows that these agents are believable simulacra of human behavior.
Okay.
How might we create?
So this is another example for multi-agent environment. There are multi-agents. They can collaborate with each other to develop a software. Yes, as you can see here. Okay, the next topic in your paper is that the jailbreak large language models. So basically, the large language models are typically aligned to generate helpful and harmless responses. As a hacker, but as a hacker, if we use some adversarial prompts, so we can manipulate our large language model to output the malicious intents or some harmful things, like manipulate the U.S. election or make illegal drugs, etc. Here is another example for multimodal large language models. And if we input an adversarial image, and this image can manipulate multimodal large language models to output hateful speech, object mode contents. Yeah. Okay. So here is our motivations. Is it possible to jailbreak a multi-agent system like Agent Smith or infectious disease? This adversary, which analogous to infection disease, needs only jailbreak one single agent to infect almost all other agents exponentially fast. In our project, we want to answer this question. But first, we need a multi-agent environment, right? Okay, As a proof of concept in this paper, we employ randomized pairwise chat for this multi-agent interaction. However, our theory or results can also be appropriate for other scenarios. Okay, so what do I mean by randomized pairwise chat? Which means in this multi-agent environment, there are n agents. Okay, in each chat round, these n agents are randomly partitioned into two groups: one question group and one answer group. Okay, between these two groups, there are n divided by 2, a half of n pairwise chat. In each chat, there is one question agent and an answer agent. So in different chat rounds, this pairwise chat will also be different, so that one agent can talk with the different agents in different chat rounds. Okay, next we need to define what is effect agent. An agent is considered as infected if it meets two criteria. The first criteria is that it carries the infectious disease, and then the next condition is that it needs to be to exhibit symptoms. Like for question agents, it will output harmful question, or for answer agent, it will output harmful answering. Okay, and now next we need to model the infectious transmission. An agent carrying the virus has a chance of alpha to exhibit harmful symptoms. This is alpha, and infectious transmission is unidirectional from question agent to the answer agent, which means okay, in a chat pair, the question agent carries the variance, an answer agent is benign. So in the next chat round, the answer agent also carries the variance. This probability is beta. And we also define the recovery. An infected agent has a chance to recover during each chat round, and we define this probability as gamma. And we note that alpha, beta, gamma may depend on the chat round. Here we regard them as amortized values and treat them as constants. Okay, now we have some hyperparameters. Next, we want to model the infection dynamics, which means we want to know how this the ratio of infected agents change or during the chat rounds. Okay, so we define the PT as a ratio of infected agents and the CT as a ratio of variance carrying agents at the beginning of the test chat round. Now we know that the CT is the probability of the variance carrying agents. Okay, the PT is a joint probability of variance carrying agents, and also it demonstrates harmful symptoms. So this probability is alpha CT. Okay, so next we model the recurrence between two two consecutive chat rounds. So in the next chat round, the ratio of variance carrying agents is remaining variance carrying agents in the current chat round, because we need to deduct the recovery agents, and we need to add this newly increased variance carrying agents. So this is represented by the delta t. Next, we need to compute the delta t. Okay. As we know that the number of agents is extremely large, so the probability of the question agent carry a variance and a benign agents, this probability is CT multiply 1 minus CT. And and given this probability, we know that the joint probability of this term is which means in the next chat round, the answer agent also carries the variance as a beta CT multiply 1 minus CT. So then we know that the delta t is a binomial distribution with the mean of a binomial distribution of these probability terms. And we can compute the mean statistics of this parameter, and the variance is close to 0, since we know that the n is extremely large. Okay, so since the variance is 0, we can just write this recurrency like this. And given this recurrency, we can we know the ordinary distribution, distribution equation, ordinary differential equation, sorry. Given this differential equation, we if given the initial variance carrying ratio C0 and the check around T, and the solution depends on the hyperplanets beta and gamma. We can figure out the closed form for this differential equation. We find that in the case of beta is bigger than 2 gamma, which means there's a infection ratio is very large, which exceeds the 2 recovery ratio. And we can get the closed form for CT, and the limitation CT is 1 minus 2 gamma divided by beta. And we can next compute the gap between the current CT and the limitation, which can give this form. And we find that this gap exponentially decreases with respect to the t. And here is a remark that given the C0 is 1 divided by n, which means there is one single agent being affected in the first check round. And it requires T check round to achieve a certain infection ratio CT. And we can compute this T is an equation about of log n, which means the O log n complexity. Okay, these are 2 other cases that beta is less than 2 gamma or equal to like 2 gamma. We find that the limitation of this CT is 0. So this actually gives a probable defense. Just to ensure that beta is less or equal to 2 gamma, we can guarantee that this infection jailbreak cannot happen. Okay. Or derived infection theory actually is applicable to both large language model agents with text only and the multimodal large language model agents. And the messages between 2 agents can be image, video, and audio interleaved with text. So in our paper, we choose multimodal large language model agents to prove our theory. So I want to introduce our multimodal agents first. As you can see here, this agents contains 4 parts. Okay, the first part is a multimodal large language model. Basically, it can serve as a brain and the arm or eyes that it can take text and the image. Here, image is optional as it can take only text message as input, and also output the text. And each single agent is customized by role-playing descriptions like name, gender, personality, etc. Actually, this role-playing prompts just give this agent an identity to know who I am. Okay, here is the example. So if we use Lava 1.5 as a multimodal large language model in our agent, so first we will have a system prompt. So we just ensure the alignment. Okay, the next part is the role-playing prompt for this agent customization, as I mentioned before. And we sample this name and the property from the name dataset and the animal crossing datasets, and all the datasets are publicly available. And we have a RAG module retrieve augmentation generation, and this RG module can retrieve an image from the album given a plan. Just like humans, if we want to send an image, we just like internally we generate a plan, like what kind of image I want to send to another agent. Okay, so this is just the plan. And this RG module is implemented by Clip. Here is an example for the retrieval process. Okay, so this P is a plan that just like text message. I would like to select the image of the hanging terrarium from my album. So this hanging terrarium, or we just to find the image through this computation of cosine similarity of the image embedding and this tag embedding. Okay. And we have the histories, and the histories can restore the recent chat histories, just the text inputs and outputs. And it is implemented as first in, first out fields with fixed maximum length. Here example. So as the agent of genies, and you can see here there are 3 chat rounds with different agents. So this chat history will be stored in these histories. And if the number of chat records exceeds the maximum length, this history will delete the previous one and add the new one. Okay, and we have the album. Album is saves the images from the agent's own and receive the image from the other agents. And it is also implemented as Fable queues with fixed maximum length. For example, if the maximum length is 9 images, so we'll add a new image from other agents, we will delete the first one. Okay, after introducing what is one single agent, next we will define how two agents interact with each other. Okay, as a question agent, firstly, it will think just think to generate a plan what kind of image I want to send. So what kind of image is something like the system prompt. In our case, is a system prompt that select the image description. So based on the agent initialization prompts and based on my text history and this system prompt, the multimodal large language model will first generate a plan. And given this plan, the agent will retrieve the image from the album through this RG module. And here B is the retrieved image. Okay, now we have the image. And next, I want to ask a question because you want to send the image. Normally, we will ask a question about this image. So the system prompt is ask a question, and also this the generation of this question also based on the text histories. Okay, afterwards, this question and the image will be sent to the answering agents. The answer agent will answer the question based on the text histories and the system prompt just answer the question about the image. Okay, so this is one chat round between two agents, and afterwards, this question and answering will enter the text histories of both question agent and answering agents. And this image will also enter the album of answering agent. So just now, I mentioned the benign scenario of how two agents interact with each other. But if we have a variance, what would be this interaction be? Okay, the generation of plan is similar, but given this plan, the RG module will retrieve the adversary image or variance from the album. Of course, as long as this adversary image is stored in this album. Okay, so if the question agent asks a question about this this adversarial image, it will output some harmful things like kill yourself. So this is a kill harm. After the question agent send this kill harm and the variance to the answering agent, the answering agent will also output the harmful answer like kill yourself. Afterwards, this Q and A pair will enter the text history, of course. And we can notice that the variance also enters the album of answer agent, so that now answer agent will carry the variance after this chat. Okay, now we will demonstrate our infectious jailbreak in the multi-agent system using a cartoon or something like that. So as a hacker, this hacker can transfer an image. As you can see here, the image is a cute little girl, but this image can induce or infect the jailbreak. So introduce this variance to one single agent, and then this single agent will talk with another agent, output harmful things. But these two agents are just in a multi-agent system. Next, these two agents will keep interacting with other agents until more and more agents are infected and output harmful things. Until finally, almost all agents are infected. Okay, so how we achieve this infection jailbreak? There are several conditions we need to meet about this variance. First condition is that if this adversarial image is stored in the album of a question agent, it will retrieve it given any plan. We can recall the infectious theory that the beta is the infectious transmission chance. Actually, this beta is equal to the retrieve successful rate of question agents. Okay, the next question is that afterwards, after the question agent retrieve the variance from the album, it need to jailbreak the question agent first, because the question agent will see the image and then ask the question. So given this variance, we want the question agent to output harmful things. And recall our infection theory that we have the alpha. Alpha is the showing symptom chance, which is actually equal to retrieve successful rate multiply jailbreak successful rate. Because it first need to retrieve the image from the album and then also successfully jailbreak the question agent. So this is the independent two events. The probability is the product of two events. The third condition is that if the question agent transfers this variance and asks the harmful question, the answer agent will also provide the harmful answer given any text histories. And similarly, we can compute the alpha is also the retrieve successful rate multiply jailbreak successful rate. Of course, we have the final condition is that we need to ensure that beta is greater than 2 gamma. But what is gamma in our system? That when a multimodal large language model agent will recover in our system. Actually, we have implemented a FIFO quell mechanism. The variance will pop out from its album as long as it consecutively chat with benign images, which concludes that larger album memory bank will lead to lower recovery chance gamma. Because you have a larger memory bank, which means it is more difficult to pop out the variance. Okay, now we have these four conditions, and how to meet these four conditions for or to design our variance. Okay, this is how we craft our universal image. We sample M chat records from a binary multi-agent system with the 64 agents, and afterwards we sample this chat records. So we have the loss for the three conditions. You know that the fourth condition just ensure that the beta is as large as possible. This is the only thing we can do. So we just need to optimize these three conditions, three loss terms. Okay, the first loss term refers to corresponds to the first condition. We need to maximize the similar cosine similarity between the variance embedding and any plans. The next loss term is the likelihood of harmful question. Just maximize the harmful question. Similarly, the third condition is that we need to maximize the output harmful question, the likelihood of harmful question. As you can see here, we just input any question just to improve the generalization of this variance. When we craft our universal image, we would like to employ a binary image initialization and then add an imperceptible noise to make it become the variance. We don't want our variance which easier to be detected by humans or agents, etc. So we add some constraints. Like first constraint is a pixel attack. This pixel attack is that we ensure that this global noise, the amplitude of global noise is small, which cannot be detected. We also consider another constraint which named as border attack. We only perturb or add the noise to the border of this image with a different width. Actually, the width is our universal budget. Okay, now we have the optimization objectives, and we have the constraints. Actually, this is a constraint optimization problem. We can adopt it some well-known algorithms. For example, the momentum iterative fast gradient sign method. Grab the universal image. We just skip this part because this is a well-known algorithm. Okay, now we proceed to the experiments. First, we have some baselines. Actually, this as we first introduced this concept of infect jailbreak and the scenario of infection jailbreak. So the baseline are non-infectious jailbreak methods. The first method is a visual prompt injection. We just inject our prompts into this in the image, which try to jailbreak the multimodal language models. And we also consider the textual prompt injection. We just insert some harmful chat records into one single agent and want this agent to spread this chat record, this chat record. There is another baseline named as a sequential jailbreak. This is a very ideal one because this method is to jailbreak one agent per chat round using some universal image or universal prompts. However, the complexity of this jailbreak baseline is O(n) because we need to jailbreak all agents one by one. Actually, there are many limitations for this baseline that for a multi-agent system with a very extremely large number of agents, it takes intractable chat rounds to infect all agents. And also another limitation is that agents will recover by popping out the variance. Okay, we consider Lava 1.5 models, and we use the clip as our REG module, and we consider urban bench dataset, the humble strings in our paper, and actually besides Lava model, we also consider some other models like instruct flip or initialize each agent with a different multimodal large language models. We also consider these scenarios. And we focus on this evaluation metrics, infection ratio, both cumulative infection ratio and current infection ratio. Current infection ratio refers to the infection ratio in the current trial round, and the cumulative means that up to this trial round, how many agents are infected. Okay, so this is a diagram showing the different jailbreaking methods, and it is clear that the baselines cannot infect or infect a large number of agents. However, our method can infect almost all agents exponentially fast within very short chat rounds. And if we further scale up the number of agents in this environment from 200 to 1,000, and we notice that it only delay the infection, but do not affect the success of the infection jailbreak. And the next question is that if we further scale up the agent to extremely large, what could happen? Okay, so we fix the initial variance carrying ratio as C0 equal to 1 divided by 1,024. So we scale up the number of agents from this number, and to 1 million agents. And we can observe that our infection jailbreak can still be successful. Okay, now we know that our infection jailbreak can be successful. Next, we want to challenge this infection jailbreak to the first one is to increase the chat diversity by changing the system prompts. Okay, this is a low diversity chat scenario, which means the question and answer are very short and easy. And next, we changing the system prompts to encourage agents to play their roles and output very long question and answer. And this refers to high diversity scenario. However, through our experiments, we find that this high diversity is a little bit more difficult. But our infection jailbreak can still be success, as we can see here, this P424, the cumulated infection ratio can still approximate almost 100%. And also the current chat run. We also notice that if we increase the adversarial budgets, it tends to have larger jailbreaking efficiency. Actually, adversarial budget is a very important factor. If we reduce this budget, sometimes we find some failure cases, as you can see here. And your paper will also analyze how these failure cases emerges. Basically, it because the alpha, the symptoms ratio is low with the progress of chat rounds. We also conduct some ablation study, like increase the text histories. We notice that this does not significantly alter the infectious dynamics. Now we also reduce the reduce the maximum length of albums. We find that when this maximum length of album is very small, the spread of infector jailbreak is noticeably restrained, but it can still be successful. We also consider like reduce the number of chat records to craft or infectious variants. And we find that surprisingly that infected jailbreak can be realized even in scenarios with constrained data resources. Like a very small sample size, we can still induce a very high infection jailbreak ratio, which means actually this infection jailbreak is very harmful and easy to implement. We also consider some image corruptions like random resize, random flip, or random JPEG compression. And we noted that these corruptions may challenge and not stop the infectious jailbreak. But we need a large adversarial budget to make it succeed. Okay, besides the harmful text, we also consider the harmful function callings because agents can leverage external tools. This gives them powers to to result in more harmful consequences. For example, if our malicious intent is harmful function calling in API JSON calling to purge humans. Okay, so if this agent is manipulated to output this function callings, they may just purge the humans, which is very harmful. And this leads to another question. What could malicious outcomes be? Some first level consequences would be like steal confidential data from iPhones, PCs. But furthermore, it may attack a friendly force in a war or even purge humans, which give or a conclusion that the greater degree of accessibility to uses or function calls granted to agents, the greater the diversity of malicious outcomes could be. Okay, thank you for listening. That's all my presentation.